Well, good afternoon. Thank you for coming today, and we're about to start our seminar, but before we do, please be aware of the exit signs in case we need to leave the room on short notice. And those that are on the internet, we really strongly encourage you for the Q&A to send your email questions, and the email address is found at the bottom of the monitor that you're looking at. Send your email questions at first opportunity so we can have time sufficiently to answer your questions. So with that, Toshi.
Hello, everyone. Welcome to the headquarters of California Environmental Protection Agency, and thank you for being here and on the air listening in on California Air Resources Board's research seminar. My name is Toshihiro Kuwayama from the ARB, and I am the contract manager of the research project that is being featured today. Before moving on, I will be providing a brief background on ARB's Sustainable Communities Research and a brief overview of the importance of today's featured research project and how it is pertinent to ARB's programs as we progress towards achieving sustainable communities in California. At the ARB, we help develop strategies to promote sustainable communities, which are neighborhoods with safe, reliable, and affordable transportation choices to improve air quality, health, and reduce greenhouse gas emissions. Sustainable communities also emphasize on equitable and affordable energy and location-efficient housing options, as well as improved access for quality employment, education, and other resources and services that makes its surrounding environment safe and vibrant. The Sustainable Communities and Climate Protection Act of 2008, or SB 375, supports the state's climate action goals to reduce greenhouse gas emissions through coordinated transportation and land use planning with goals of more sustainable communities. SB 375 directs ARB to set regional targets for reducing greenhouse gas emissions and establishes an approach to involve cities and counties in development of regional plans to reduce vehicle miles traveled with strategies such as shifting development and population growth along transit corridors. However, policies to encourage greater residential density around transit corridors, such as in transit-oriented developments, may lead to unintended effects of greater pedestrian exposure to roadway pollutants. Therefore, it is important that implementation of SB 375 is consistent with ARB's criteria and toxic pollution exposure reduction policy goals. To help achieve sustainable communities in California, the ARB is focusing its research efforts on how we plan, build, and interact with built environment can impact the air quality, health, and the greenhouse gas emissions. ARB's sustainable community research focuses on land use, transportation planning, green building, and cool communities to evaluate the potential reductions in greenhouse gas emissions, air pollutants, and urban heat island effect. All of these are tied to the advanced progress in combating climate change needs to satisfy the requirements of SB 375 and Global Warming Solution Act of 2006, or AB 32, all while meeting the current air quality standards. In recent months, the findings from ARB's Sustainable Community Research Projects were synthesized and were published online as technical advisory, supplementing ARB's Air Quality and Land Use Handbook, a community health perspective. It is intended to provide planners and other stakeholders involved in land use planning and decision-making with information on scientifically based strategies to reduce exposure to traffic emissions near high-volume roadways in order to protect public health and promote equity and environmental justice. Office of Planning and Research will be using this technical advisory to develop general plan guidelines as a basis for future land use planning and developments. ARB's Sustainable Communities Research plays a critical role in reducing exposure to traffic-related pollution, and future research studies will continue to improve our air pollution mitigation strategies to protect the environment and the public health. In today's research seminar, Dr. Suzanne Paulson and Dr. Nico Schulte will be presenting the findings from ARB's research contract number 12308, titled Identifying Urban Designs and Traffic Management Strategies for Southern California that Reduces Air Pollution Exposure. This research seeks to help minimize the pedestrian exposure to air pollutants by advancing the understanding of factors controlling spatially variable pollutant concentration around roadways in transit-oriented developments. The results from this project will provide decision support tools and information ARB could use to guide transportation and urban planners to protect public health pursuant to ARB's mission and goal of protecting the public from exposures to toxic air contaminants and reducing GHGs. With that said, I would like to introduce Dr. Suzanne Paulson and their co-PIs and provide a little bit of their background. Dr. Suzanne Paulson, the principal investigator, earned her BA in chemistry from the University of Colorado and a PhD in environmental engineering sciences from California Institute of Technology. Dr. Suzanne Paulson is a professor in the Department of Atmospheric and Oceanic Sciences and a professor in the Institute of Environment at UCLA, where she serves as a director for the Center of Clean Air. She also serves as an airport commissioner for the city of Santa Monica. Dr. Suzanne Paulson's current research studies the impact of naturally occurring human-made particles on public health and Earth's climate. Her research also focuses on the influence of built environment on air pollution levels in complex urban area. Dr. J.R. DeShazo, co-PI of this research project, earned his PhD in urban planning from Harvard University and a Master of Sciences in Economics from Oxford University. Dr. DeShazo is the director of Lushkin Center for Innovation and professor and vice chair of the Department of Public Policy in Lushkin School of Public Affairs in UCLA. He advises the Los Angeles City Council and the Metropolitan Water District of Southern California, among key agencies. Dr. DeShazo's recent research has focused on local public finance, regulatory reform, climate change policy, solar energy policy, and plug-in electric vehicle policy. His work also supports the California Air Resources Board and the Southern California Association in their effort to implement AB 32 and its complementary SB 375. Dr. Akula Venkatram, also a co-PI of this research project, earned his BS in mechanical engineering from Indian Institute of Technology and his PhD in mechanical engineering from Purdue University. Dr. Venkatram has over a decade of experience at ENSR Consulting and Engineering and served as the head of department at Ontario Ministry of Environment in Toronto, Canada, before accepting his current position at UCR as a professor at the Department of Mechanical Engineering. Dr. Venkatram pursues research in comprehensive modeling of systems governing air quality, theoretical aspects of small particle dispersion, application of micrometeorology to dispersion problems, and development of simplified models for complex urban systems. Professor Venkatram's current research focuses on air quality impacts of various anthropogenic sources in urban environments. Dr. Nico Schulte was a graduate student under Dr. Akula Venkatram, who is also today's speaker. He has earned his BS and PhD in mechanical engineering at UCR. He has led UCR researchers to develop the vertical dispersion model that will be discussed in today's presentation. Dr. Schulte now works at the California Air Resources Board, studying commuter exposure to various air pollutants in a large network of urban transportation modes. Dr. Schulte is an expert in particle dispersion in complex urban systems. Now with that said, please welcome our first speaker, Dr. Suzanne Paulson.
Thank you very much for that very extensive introduction of myself and everyone else. I will mention these people at the end, but I do want to point out that the people who really did the work, in addition to Nico, are Wanshik Choi, who was a postdoc on this project, Dilhar Ranasinghe, and contributions from a large variety of other people. So the guidelines for our project was to develop guidelines for, the objectives for our project were to develop guidelines for TOD planners to reduce pedestrian exposure to air pollution in urban built environments. And we were going to do that through field measurements, analysis, and statistical modeling, and also to develop a dispersion model that could be used to help TOD planners with quantitative links between variables that control dispersion in complex urban environments. So first, the introduction, a little bit about air pollution near roadways and their health impacts. So first of all, there are a variety of pollutants that come from traffic sources, and almost all of the data that I'm going to show you is going to be ultrafine particle data, possibly even all the data. But there are other pollutants that are also emitted from traffic sources, including oxides of nitrogen, volatile organic compounds. Some of those are considered air toxics. And there's also brake dust. So the NOx, the volatile organic compounds, and the ultrafine particles tend to kind of be dispersed together. The brake dust, a lot of that is heavier particles, and they don't necessarily have the same spatial distribution as the ultrafine particles. So I'm going to show you a bunch of evidence that indicates that roadway pollution is problematic for a wide variety of health outcomes. There's additional evidence that ultrafine particles probably play a role in that, but even if they don't, they're still an excellent tracer of where most of the roadway pollution is. Basically everything except for the brake dust and dust that's resuspended from vehicles moving over roadways. Okay, so pollutant concentrations near roadways vary a lot. They're extremely high, very short time scale variations in concentrations, and they vary because of a number of factors. So it turns out to be a complex problem. So first of all, there's the fleet emissions, which depends on the traffic density, the fleet composition, which changes over time, and also the driving conditions. Are cars going faster, slower? Are they doing a lot of stopping and starting, and so on? The atmospheric dispersion, including the wind speed and the direction, and how that interacts with the built environment. The atmospheric stability and vehicle wakes, as well as the topography of the roadways. Roadways are elevated, or there's hills or whatever. And then there's the built environment, the roadway geometry, the buildings, sound walls near roadways, vegetation, trees along, etc. And then a lot to do with the actual observed roadway pollutant spatial distributions has to do with the relationship between the peak and the background concentrations. I'm not going to go into in a lot of detail, but it is quite important for interpreting a lot of data. So this is a cartoon, really a cartoon. Real, not really real. You wouldn't ever really find exactly this in the real world, but it shows the three modes that we do typically observe in urban areas. Actually, pretty much everywhere. Oh dear. We see. Sorry, we see. So the area under the white curves, typically we always see these two peaks, and there's the fine mode there, and then there's the coarse mode. Coarse mode is basically a lot of the brake dust would be in there. Fine mode is present. When we're close to roadways, we see the areas that are outlined in blue in addition to the sort of white area, which is kind of the urban background. So these little tiny particles are called ultrafine particles. Ultrafine is particles less than 0.1 microns or 100 nanometers. We also see some enhancement in the coarse mode particles. That's the brake dust. So the ultrafine particles, which is what I'm going to talk about a lot, are very good tracers of roadway pollution, partly because their urban background is so low. And it's not that they magically disappear. It's that over rather short time scales, they coagulate with the larger particles and become incorporated into the larger particles. So they basically become part of the fine mode. But the fact that they have such a low urban background after several hundred meters or a few kilometers, depending on the time of day, away from roadways, means that they are quite convenient to measure and a very strong signal for roadway pollution. So this shows some electron micrographs of different particles that were collected. These were actually all collected on a street outside one of the buildings at UCLA. And you see kind of the variety of particles that we inhale. Actually, the ones in the upper right, the diesel exhaust, those were collected in my lab. So it varies from very tiny particles to larger particles, and you can clearly see this sort of result of these particles coagulating with each other. So we get these very complicated looking particles with lots of different stuff inside them. Particle size matters for a lot of reasons, certainly in terms of their dynamics in urban areas, but also where they deposit in our lungs. And this diagram has three areas: the upper airways, the tracheobronchial areas, and then down in the lower lungs in the red. And the ultrafine particles and the fine particles both manage to penetrate fairly effectively into the lower lungs. And if particles are collected in the alveolar region of the lungs, then the clearance rate is very slow. So particles have a lot of time to do their damage. This is a close-up of one of these alveolar regions, and it shows in red a 1 micron particle and a 0.1 micron particle. The 1 micron particle is too big to pass through the cell membranes and tissue structures, but the ultrafine particles are similar sized to viruses. We've all had personal experience with viruses penetrating through cells and getting from our lungs or wherever they entered our body throughout. So ultrafine particles have a similar ability to translocate throughout the body, which is special amongst all the particles. So there are lots of studies documenting that particulate air pollution causes health effects. A lot of that is PM 2.5 results. But these are results that are specifically looking at what proximity to traffic does to you. So we don't have any community measurements, widespread community measurements of ultrafine particles or other roadway pollutants that we could do an epidemiological study on. So instead, we're using just proximity. How close are you to roadways, and how much, so people who are living close to roadways presumably for the most part have higher exposures to roadway pollutants. There are lots of different health impacts that seem to accrue to people living near roadways, especially in more sensitive groups. These are just some of them summarized here. They include prenatal impacts. This is a series of studies conducted by my colleague at UCLA, Beata Ritz, and coworkers. And they show, for example, that women living near roadways, particularly with high concentrations of heavy-duty truck traffic, have increased risk of premature delivery and low birth weight babies. Low birth weight and premature delivery is an indicator of overall lifelong health to some degree for children. Asthma prevalence has been observed in a couple of studies in California and many other studies around the world, including in Southern California and in the Bay Area. For adults, there are higher levels of acute respiratory diseases, including asthma, chronic obstructive pulmonary disease, pneumonia, and lung cancer, and also heart attacks and strokes. And there seem to be other incidences or other associations with additional astonishing array of other health impacts. So in our study, we used a couple of approaches, basically a mixture of stationary and mobile measurements. And we made measurements in the Southern California area, many of them around downtown Los Angeles. All of the dots show the locations. Some measurements were made in Beverly Hills, and some other measurements made in Temple City. So they're all kind of in the coastal plain. Temple City is a little bit closer to the mountains. And then Riverside is not quite to scale. It's actually a little bit further off. Made in Riverside. The many of the mobile measurements were made with ARB's mobile platform. One of ARB's mobile platforms, the Southern California one, and it has a wonderful array of instrumentation, including a fast mobility particle sizer and CPC, and a variety of gas measurements as well. And it has a anemometer on it, although we can only use the anemometer when the vehicle is stopped, and GPS, obviously. And it's not on here, but we also sometimes made measurements with a disc mini. There were also a number of stationary measurements. You see Riverside largely used stationary measurements. They used a collection of condensation particle counters. And they also deployed 3D sonics that were able to make measurements continuously because they were not on a mobile. Okay, so here's a roadmap for the rest of the talk. So next, I'm going to give the microphone to Nico, and he's going to tell you about results for street canyons that they put together at UCR. And then after that, I'll take the microphone back, and I'm going to talk about 4 studies that we've done at UCLA. And one of them is a little bit more methods, but it was quite a bit of method development, and so it's a paper on its own. So looking at issues dealing with processing mobile measurements in order to get really high spatial resolution information out of them. And then I'm going to tell you a little bit about a microdynamics model, the development of which was led by my colleague J.R. DeShazo and the student Lisa Wong. And that can actually predict second by second concentrations along the street. And then in a little bit larger view than the street canyon view that Nico's going to talk about, I'm going to talk about neighborhood view analysis of our monitoring data to look at more heterogeneous street environments than the street canyon environment, and look at a little bit larger scale, on the scale of several city blocks. And then finally, I'm going to finish with a study that we did looking at the location of bus stops and if they're optimally sited with respect to exposure. And then after I summarize all that, then summary for planners. So I hope you're planning to be here for a while.
All right, so I conducted some of the work on developing models. So I want to just give a brief overview of model development in these slides. Talk about models that estimate the near road concentrations of traffic emissions when they're building. And for the details, I want to refer you to this journal article and also to the final project report. I'm going to skip over this first image in the interest of time, but I wanted to kind of give a preview of one of the major results. So in this bottom figure, I plotted the concentration magnification, which this is simply the ratio of the concentration that you would expect based on the models we developed next to a roadway with a given building height, with the given height of buildings next to the road, to that with no buildings next to the road. So this gives you kind of an idea of the magnitude of the effect that we're talking about and the impact of increasing the building height next to the roadway on the concentration of the traffic emissions near that road. And so in these next slides, I just want to go over, I'm very briefly going to give an overview of our approach and some of the field work that we did and the development of models to interpret those, and then also give some practical guidance on how these results can be applied by planners. So the way that we formulated this is our objective was to develop models that account for effects of buildings next to the roadway that link traffic emissions to the expected near road pollutant concentrations in that road. And so we validate these models with field measurements, and then these validated models can be used to conduct numerical experiments that would be impossible in the real world. And so the models that we developed are useful to evaluate the impact of transit-oriented development designs, evaluate the impact of mitigation measures that seek to reduce traffic emissions. So our approach for this study is we really start out with really formulating a model at the beginning based on past research. We use that to design the field measurements, conduct the field study to collect observations, evaluate the models, and then modify them based on the data and the evaluations to develop improved models. And so I just want to emphasize that these models are really fundamental to all the steps of this research. So we we did quite a lot of model development and evaluation, and eventually we settled on what we call this vertical dispersion model, or VDM. And I've shown kind of the basic equation that relates the traffic emission rate, the building geometry, and meteorology with the expected concentration of those traffic emissions. And so this equation looks simple, but we did quite extensive evaluation with observations, and we tested many alternative models. And so the development really was not simple at all. And I would refer you again to the journal paper for a detailed derivation. But just kind of to get a physical understanding of this, this equation's describing vertical turbulent transport from the surface to the building rooftops. And the length scale for that vertical turbulent transport is the smaller of the building height and the street width. And so by going through the derivations, we find that the aspect ratio of the street, which is the ratio of the building height to the street width, primarily determines the magnitude of the concentrations of traffic emissions in the street. So this right away raised the question of how we define this building height, because for real world cities, especially in LA, building heights can be extremely variable. There's spaces in between buildings. And so in order to apply this to real world situations, we needed to define this concept that we call the area weighted building height. And so this is simply the height of the buildings next to a roadway, where the average of the height of the buildings next to a roadway, where their heights are weighted by the length of the building along the street. And so you can see in the bottom left figure one of the field sites in Los Angeles where we collected observations. There's this sometimes significant space between buildings and the heights are extremely variable. And so the way that we would apply these models to our field data is that we would compute this area weighted building height for the street. So this gives us this one number that we use for the height in the dispersion models. I just want to emphasize that this is a critical component of the models. So I want to kind of switch tracks and go into the evaluations that we performed. So we have, on this slide, I'm showing evaluations of this vertical dispersion model with concentrations of traffic emitted ultrafine particles from the Los Angeles field sites. So on the top right, you can see the condensation particle counters that we use to make these measurements. The bottom left shows a scatter plot comparing the observed and the modeled concentrations. And this legend and these different colors indicate the aspect ratios of these field sites. So you can see the aspect ratio range from 0.2 to 2.2. The right figure shows a quantile plot that compares the observed and modeled concentrations. Based on this evaluation, we feel that the VDM gives like an adequate description of the near road concentrations. And this encouraged us, so we proceeded to conduct further evaluation with additional observations. This shows evaluation with measurements of traffic emitted carbon monoxide that we conducted in Riverside in August and September of 2015. So again, I'm showing on the bottom, you can see the instruments next to the road and at the rooftop sites that we used. And also I'm showing, again, the scatter plots and quantile plots. Oh, sorry. So this legend here shows some model performance statistics. So if you want to know more about these, look at the journal article or look at the final report. But based on this, again, it seems like the model performs quite well, and seems like it's adequately capturing the essential physics of the dispersion in the near road environment with buildings next to the roadway. We performed additional evaluations. I'm going to skip going over the details of this in the interest of time, but essentially this kind of reinforces the idea that VDM captures the essential physics of dispersion. So we have this validated model, and but one difficulty for using this is that there's several model inputs that we need to estimate for kind of practical applications. So we needed to develop a method that can be used to relate routine meteorological measurements which are commonly made at airports or sites outside of the urban area, with the model inputs that the VDM uses. So here I'm showing an example of this is kind of a snapshot of the Riverside site, and you can see this red line that I've drawn connects an airport site where we can get routine meteorological measurements, and the downtown urban site where we conducted the concentration measurements to evaluate the models. And so we found that a internal boundary layer model that relates, that is useful to relate these airport routine measurements with the model inputs required for the dispersion model. We conducted some evaluation of these models as well, and so the details are available in the journal article and the final report. So in summary, the VDM captures the essential physics of dispersion. It helps us understand what the effect of changing the building heights near the roadway are on the near road pollutant concentrations. And based on this model, we see that the primary variable that controls the magnitude of these concentrations is the ratio of the area weighted building height to the street width, or effective aspect ratio. And so this suggests that this effective aspect ratio should be limited to reduce exposure to traffic emissions in the elevated concentrations of traffic emissions. So before I finish up, I just wanted to give to show this how this could be used in practice, and also show a major outcome of this project. And so we translated the VDM model into a software tool that a planner could use to kind of get to practically apply the model results. So this software tool has the option of where the user can enter preset model inputs to get a quick estimate of what the model is predicting, and also it allows the user to enter detailed inputs for specific sites that they want to study. And so one very useful way that this can be applied by a planner would be to combine this tool with the dispersion model AirMod. So AirMod is the EPA regulatory model that is widely used to estimate the impact of point source and roadway emissions. So a planner could combine AirMod with VDM, and I've given kind of like a flow chart of the steps involved. So a planner could develop project level emission estimates for transit-oriented development, use AirMod with the standard urban options to compute the impact of the roadway, but this is neglecting the effect of the buildings next to the road on the concentrations. And then they can compute the building inputs required for VDM from digital elevation models, which are readily available. And then they can use this VDM software tool, which will calculate the enhancement of the concentrations that's expected due to the presence of the buildings next to the road. And so by combining these tools, you can get an estimate of the effect of the buildings on the concentration. So there's a link on the bottom for where you can download the model, and I encourage you to try it out.
All right, I'm back. All right, so a little bit about processing mobile data. So for the mobile part of the study, we did measurements in a cloverleaf pattern, which is shown by the red line in this diagram. And this particular location is a site in downtown Los Angeles. It is actually the only site that's really really kind of has a street canyon. These are quite unusual in So the mobile data gives space. So you're driving along, and you kind of got to obey what the traffic laws are. You need to stop when there's a stop sign and do all those normal things and not get run over and stuff. As a result, the mobile data gives you spatially heterogeneous measurements. Sometimes you get 30 measurements in one place when you're sitting. Most of the measurements are made every when you're sitting at a stoplight, for example, sometimes even longer. Sometimes you get one every 20 meters if you're going relatively fast. So simple averaging of mobile data after correction for the wandering GPS signal, which is another problem, but not that hard to solve, of measurements in urban areas where you lose the GPS signal sometimes. Sometimes simple averaging of the data ends up literally looking like a trail of confetti if you use color and concentrations. It's just a mess. And then there's the other question of how many runs do you need? So there are lots of mobile measurements being made. It's just growing in popularity. And so I think it's a really valuable thing to look at. How many measurements do you actually need before you get a representative? So these plots illustrate a couple of those problems. The one on the left shows the problem of the wandering GPS signal. And then the one on the right shows you the red dots are the actual measurements for that particular data set. And there are gaps in between them. Sometimes the gaps are, you can't even see them. Sometimes they're fairly wide. So what we decided to do is to use basically a line reference system. So on every line, every street segment, we put a reference point, and you can make these as wide as you want. We really want our spatial resolution. We're getting really high frequency data, and we want to get high spatial resolution out of it. So we want that value x to be as small as possible. And so on this reference system, every time you drive down the street, we make sure that every reference point along this, so if they're every 5 meters, every point is going to get a measurement. Because if they don't, if there's no value there, then some other run, the other time you run down the street, that other run will get overweighted at that location. And if you have 30 data points at one location, and only one the next time, then the time when you get 30 points in one run, when you stop, will be overweighted compared to the when you just one measurement. So we want one value for each pass for each data point. So, so what we do is if we have a whole bunch of data points at a particular location and run, we just average them all together. And if we don't have any data point, then we interpolate one. And we figured out a really good way to interpolate one. In the plot on the right, there are the blue dots are the interpolated dots. And I think that, you know, looking at it, you're easily convinced that that's where the value should be. And then we also looked at what kind of spatial resolution we can get out of this 1 second data without interpolating too many points. And the technique we use to interpolate is called a piecewise cubic Hermite spline. This shows the number of data points that get interpolated. So if we go down to about 5 meters, we only have to interpolate about 15% of the data points. If we go below that, then we got to interpolate a lot more, and then maybe that becomes unacceptable. So this is a result from that process. We can get this very, very high spatial resolution map of 4 large city blocks in the middle of downtown Los Angeles. This particular data has all of the spikes in it from high emitting vehicles. So trash truck goes by, we see this gigantic spike. And what you see from this plot is the red areas, the higher concentration areas, tend to be where vehicles are accelerating around intersections. We can also take out the spikes. We have some good quality, high fidelity data processing techniques for that. And then we begin to see the effects of the built environment, which I'll show you in a second. But this shows the number of repeats that you need to do in order to get representative data, but with the caveat that these are for measurements that were made all at the same time of day and with similar meteorology. So this is not going out any random time throughout the year in a city in California. This is just the morning runs, and the weather was well behaved. We were having an onshore flow. We were having actually maybe a weak nighttime land breeze, but we weren't having, like in Southern California with Santa Anas. We weren't having Santa Anas, or there wasn't a storm or whatever. So, so under those conditions, so fairly well behaved and reproducible sort of mesoscale meteorology, then this shows the relative error if you just average 2 runs, 3 runs, and so on. And you can see that the relative error starts out to be around close to a factor of 2 initially, and then it comes down, and then you have to sort of decide what kind of error you can tolerate. And if you want to get to, like, I forget exactly where these are probably like plus or minus 20%. So there's still a somewhat significant error there. For that, you need to do between 16 and runs or so, depending on whether it's the morning runs or the afternoon runs. So you need a fair number of runs to get representative data, and that's for confined meteorological conditions. Okay, so this is this shows maps of the same area for morning and afternoon, and with all the spikes and with the spikes removed on the left and the right. So in the morning in Los Angeles, the atmosphere is usually neutral to slightly stable, and in the afternoon it's unstable. So that's why we separate out the morning from afternoon. And when you look at the plots on the left with the higher emitter spikes, for the most part you see accelerations around intersections. When you take those out, you start to see more of the effects of the built environment. And if you kind of look in general, if I can get this, things like over here we have low concentrations. That's an area where there aren't any buildings. Where there are taller buildings, there tend to be higher concentrations. This effect here actually is a classic street canyon flow where the wind is going in prevailing direction, and the street canyon flow actually goes in the opposite direction. So you see higher concentrations on the side of the street, on the opposite side, basically on the upwind side of the street, because of the way the vortexes form from the flow in a street canyon. So you can see some more interesting features of the built environment. Okay, so the data where I'm showing you data that's highly spatially resolved in some of the coming results, that's how we processed it. Okay, so now I'm going to switch to the microdynamics model. So it's a quite interesting approach. JR is largely trained as an economist, so it's a more sort of econometric approach. It's quite interesting. So this, the data set that we used for this study was actually an earlier data set because it was kind of a initial proof of concept, and we needed to get it going while we're making the field measurements. So we started on this earlier data set. And this data set is a transect that goes up and down a street that's just south of downtown Los Angeles called Broadway. And measurements were made in 2008. There are about 7,000 observations of ultrafine particle concentrations. And so the idea, the motivation for taking this approach is to answer some of the questions. How much of the observed variation in ultrafine particles can it be attributed to each explanatory variable? And there are a lot of them. I'll show you them in a second. And how accurately can we measure the relationships? How much of the observed ultrafine particles can be explained by the collection of variables that we're using? What local factors are we leaving out? And then we're also going to use the model to predict and simulate concentrations in principle more configurations than what we have. So we have, it's mostly focused on around intersections. And so if you envision a picture of the mobile platform, which is the little blue car on the left, coming up to an intersection, it's going to be facing oncoming traffic, traffic crossing from the left, and traffic crossing from the right. And we have on the mobile platform a video camera facing out the front of the camera. So undergraduates at UCLA went through every minute of every one of those runs and recorded where every vehicle was that were in the field of view for every second. And that took a long time. And it was very painstaking work. The result of that is follows. So the factors that are being considered are the emission sources, i.e. the vehicles, the atmospheric conditions, although we have actually very little variability in that metric, the built environment, the position of the mobile platform, and there's also a constant in the model for the background concentration, and using a regression model. These are a couple of the results, and the red line is the predicted concentration, and the blue line is the actual concentration. So you can see that a very high temporal resolution and directly related to that spatial resolution, we're getting a very good match to the observed concentrations. It tends to underpredict the peak concentrations. So these are high emitters that are going by, and they're obviously higher than the average high emitter. So they're going to always undershoot those. So we have three types of findings. One is the cumulative impacts of the different factors on the streets, which ones are most important in this analysis. The dynamic ultrafine particle patterns associated with common traffic events, and then the predicted free flow versus stop-start UFP spatial temporal dynamics. So the first one, the cumulative impacts of factors on the street. So how much does each of the factors explain the variation? So that is estimated by taking the variable of interest and setting it to 0, and then setting all the other values to their mean value and looking at the difference between when that value is not at 0. And this is a dense table. But the ones in red indicate the values. So the first column is the size of the impact in thousands of ultrafine particles per cubic centimeter. And then the next one is the standard error, and then the 95% confidence intervals. You'll notice that if you look at the confidence intervals, well, first of all, some of the impacts are negative. That's what you would expect if you have a vehicle that creates a lot of turbulence. It'll mix in cleaner air from above and lower the concentrations, or if the vehicle accelerates, for example. If the 95% confidence interval crosses 0, that means that it's actually not significant at the 95% confidence interval. It may be at a slightly less stringent interval. But some of the largest effects are from medium and heavy duty vehicles, as we would expect. And also from buses, both crossing from the left and crossing from the right, and in ongoing traffic. And also being in an intersection is a really big impact. And interestingly, building height differential, so a difference in building heights on the two sides of the street. All right, so these are some time-dependent relationships as vehicles go through an intersection. So we have plots for traffic crossing an intersection when the mobile platform is stopped. And then we have oncoming heavy-duty vehicles, and then we have ongoing and oncoming accelerations from the stop position for the MMP. So the plot on the left is the change in particle concentrations as the mobile platform crosses an intersection. So concentrations are higher in intersections, the concentrations go up in intersections. And then the one on the right is the impact of a heavy-duty vehicle coming from the other direction, so an oncoming traffic. So this is interesting. It actually increases the concentration initially, and then it goes down, and then it goes back up again. So there's a competition here between the effects of the vehicle wake. A large vehicle will induce a rather large wake and mix in fresher air from above and the emissions from the vehicle itself. So we see kind of both of those impacts. And this is also, so the values here are the cumulative impacts. And so unfortunately, some of these the sort of dynamic impacts means that the overall impact might not be statistically significant from 0, even though A, you would expect it to be, and actually it would be at a certain point in time. So here are a couple of more events. Here's acceleration event from of oncoming traffic that initially produces a bunch of mixing and actually really doesn't increase the concentration that much as long as the mobile platform stays here. And this is actually consistent with some of the other results, which will be a little bit of a theme. Typically, you could imagine, if you think about it, that that around an intersection, concentration higher on either side of the intersection, right? The vehicles are stopped while they're queuing, and then they accelerate from there. Accelerations are associated with an increase. But they continue to accelerate as they go through the intersection. So and then there are also the sort of wake issues. It's not so obvious immediately where the highest concentrations will be. Generally, we see that they are slightly before the intersection. Acceleration plus a little bit less mixing seems to put it slightly before the intersection. And we do kind of see that here. And so this is so that's another simulation for ongoing. So one of the things that that JR with his data and his coworkers and me to some degree was answer this question or at least begin to answer in a quantitative way what the cost is of making cars stop. So I think that lots of us would think that it would be better for air quality to keep cars flowing freely, but I've made this argument in papers and felt very nervous about it because there wasn't really any quantification of that impact. So we've seen in neighborhoods, we made some measurements in a neighborhood in Los Angeles some years ago where there was a stop sign at every single intersection, and it was a really residential area. I couldn't really understand why. And the concentrations were really elevated in this neighborhood more than we expected, and we thought this is maybe because they made every single car stop at every single block, and the blocks were really short. So we wanted to quantify that, and with this model we can actually begin to quantify that. So these are some simulations where you just do free flow versus stop start. You can also ask the question, what happens if there are more or less light duty or heavy duty vehicles? So in the free flow simulation, the mobile platform cruises for 30 seconds, 225 meters. All neighborhood buildings are 15 meters high. No acceleration instances occur. It doesn't change lanes or whatever. So it's just drives through the intersection sort of. And when it just drives through the intersection, average buildings, you see a elevation actually just after the intersection. Unfortunately, the version with the little box where the intersection was in it didn't make it in, but the intersection is just after 100 meters. But when the vehicle stops right before the intersection, so it slows down, it stops, and then it takes off again, then we see very different profiles. We see higher concentrations while it stopped, resulting from vehicles coming in the other direction, and then it goes through the intersection and concentrations are much higher because it's in a fleet of vehicles that are accelerating along with it. And the one on the left is the spatial version, and the one on the right is the temporal version. This is the same simulation actually with 75% more light-duty vehicles. Light-duty vehicles are getting fairly clean, so while it made it worse, it didn't make it that much worse. Okay, so that's the microdynamics model. So this is results from another study that that my group did, looking at somewhat similar. So this is the most similar to what Nico just showed you, but looking at not a single street scale, but a neighborhood scale. And so again, for this project, we're driving in a cloverleaf pattern around 4 city blocks. And now we're going to look at the average concentration in that whole area, not just the central intersection. And these are the sites where we made the analysis for. This one is a street canyon that's quite near the one. Actually, Nico made some measurements. I'm not sure if you ever but it's quite nearby where a lot of the data, his data in downtown LA was collected. So classic street canyon. And then we have a site where there's one isolated tall building and then a bunch of open space and some much, much shorter buildings. And another site that's kind of similar, but has higher traffic. And then a site where there are actually quite tall buildings on the right-hand side, but just single-story, mostly single-story buildings and parking lots on the other side and a park nearby. And then a third site where it's all single-story buildings. There's a lot going on in this table, but what I would like you to kind of focus on is the colors. So the colors show, the red shows the highest value for that row, and the brownish shows the middle values, and the blue shows the lowest values. And if there are two that are similar, then they're both highlighted that way. So the Temple City Las Tunas site is the one that's all single-story buildings. So that one is generally lowest on all by all metrics. Except for the number of buildings. There are a lot of little buildings. The other ones are quite mixed. So they're higher in some regards and lower in other regards. But the Street Canyon site, the first one, and the Temple City site are both very homogeneous, and the ones in the middle are much more heterogeneous. So generally when you have higher traffic, you have higher ultrafine particles. If that wasn't true, we'd be like, oh my God, what's going on? Not that funny, but So we do generally see that when there's more traffic, there are more ultrafine particles, but especially in the morning, so in the afternoon, we see a fairly good relationship. If there's more traffic, there are more particles. But in the mornings, we see some significant deviations. Actually, for the street canyon, we see this kind of beautiful relationship with a very steep slope. Those are the black squares in the black oval. We see a very nice relationship, but it deviates from the rest of the relationships. And then the site with all the low buildings also deviates quite a lot. So it doesn't do that good of a job, as you would expect. So we also developed a sort of spatial metric, but this metric is looking at the neighborhood, not just at the street. And one of the things that we're thinking about is we're thinking about how to try and address built environment and produce something that can guide planners is that in around TODs, we actually really need to build density. So we want to look at in a little bit larger scale. I mean, we want people to live near transit-oriented development so that they will use it and reduce their vehicle miles traveled and make more sustainable cities and achieve all these other goals. So just saying build shorter buildings and smaller buildings isn't, a completely satisfying outcome. So, so we looked on a little bit larger scale, and with that in mind, we looked at trying to model the sort of the neighborhood pollutant concentrations, not just the immediate street, and that turned out to be well correlated to the spatial characteristics of the built environment, but it involved looking at the open space on the blocks and the actual area weighted building height. So Nico's metric, I think, is actually length weighted. This is actual physical footprint area, and the overall size of the site. So it's a different aspect ratio that we're calling the aerial aspect ratio, because it is not the traditional street canyon aerial aspect ratio, which is what Nico was using. So this actually had a quite nice relationship between concentrations in the morning. The morning, which is when the concentrations are highest, they're actually, the atmosphere is quite stable. So in many regards, the morning, what's going on in the morning is, in terms of exposure, probably the most important time because the concentrations are higher, and it's not so governed by at least vertical turbulence, because there isn't very much, because the atmosphere is stable to neutral. So the areal aspect ratio, though, did organize the data in this study anyway pretty well. In the afternoons, the vertical fluctuations of the surface winds, so the vertical turbulence, did a pretty good job of explaining the data. So when there's more turbulence, concentrations are lower. That data was not normalized to the traffic. If we normalize to the traffic, most of the data collapses to a much tighter relationship. There is this one site, though, site 2, and we think that's because there's, in the afternoon, there's more transport, and it turns out that that was not a very well-chosen site because there's a very heavily traveled surface street that's nearby that kind of messes things up. So the turbulence is kind of related to the building heterogeneity. It's not as strong a relationship as might be ideal, but the data seem to indicate that when the built environment is more heterogeneous, then the turbulence is higher, and the so both the turbulent kinetic energy and the vertical component of the fluctuations are larger. So building heterogeneity seems to be a good thing in TODs. But it does seem to lower concentrations. Okay, so the last section, the last one. Thank you for your patience and your attention. This is decay of pollutants around intersections and what is the best place for the bus stop. So one could argue that people don't spend that long around bus stops. Maybe they have a lot of time in some parts of LA waiting for the bus and waiting for it to, we don't exactly have German efficiency when it comes to some of these modes. But if you could make it better, why not? You'll potentially reduce exposure. And maybe even by a lot for some people at sometimes. So, so when you think about where to put the bus stop, it turns out that the urban planners talk about the near side and the far side. I love the far side. So if you have traffic flowing in one direction, so you're going along with traffic, then the side that you're on before you cross the intersection is the near side, and the other side is the far side. And you'll see from some of our data, if you look closely, it might be a little bit better actually to put the bus stop in terms of exposure on the near side, but there are a lot of really good reasons to put it on the far side in terms of traffic flow. And getting cars to not stop is really, really good for exposure. So plus people, are less crazy, and, it takes less time to get places. There are a lot of good reasons to put it on the far side. Basically because the bus doesn't block traffic where it's stopped. Light changes. So so we're focused on the far side. So these are some pictures of our intersections just to show that there's a lot of variety in the different intersections. They have tall buildings, short buildings, no buildings, minor streets, major streets crossing, and so on. A lot of information on this one too. I guess the thing that I'd like you to focus on most is the traffic density row. So there's also a lot of variety in terms of how much queuing there is. Some of the sites had long queues that dissipate rapidly. Some of them had almost solid traffic throughout the whole block. And some of them had minimal or short queues. Another thing that you notice is down on the bottom, it says the difference between the traffic lights and then the distance between traffic lights. And it's generally at least 125 meters, but more typically an average is around 180, 200 meters. Some of them are even longer. So if you go very far, you get into the next intersection. So this shows, there's a lot going on here, but basically this shows average profiles for many different intersections. The one labeled Beverly is actually a road called Wilshire in Beverly Hills, and that's actually a collection of 5 intersections along that road. It shows the mornings and the afternoons and the 2 different directions or 4 different directions depending on how we were driving. And then the black lines show the averages. And the reason for, initially we thought, oh, we'll just show the averages, but the thing is that the peak moves around a little bit from the different directions. So the effect of averaging all the data together means that it makes it look like the pollution is less elevated in the intersection area than it actually is. So that's why we're making you suffer through all those different curves, because if we average it, it looks like it's a pretty small effect, but actually taken individually, it's a pretty big effect. So basically what we're going to conclude is that typically, well, a lot of far side bus stops, there's still bus stops located on the near side, and when you encounter them in traffic, you'll start to notice. If you go notice it, if you go think about it, you'll be like, oh, why don't they move that to the other side? But the ones that are on the far side that I'm put in more recently are typically 20 meters. So we look at moving them to 40 meters, so a little bit further away. And if you look at that on these plots, so on the far side, so all these data are showing near side to far side, even if they're different directions, they're all near side to far side. If you move them from 20 to 40 meters, sometimes it doesn't make much difference. A lot of cases, though, it makes quite a significant difference. Waiting at those bus stops. These are even more intersections with more crazy curves. And these are like almost 100, sometimes 300 profiles averaged together. There is a lot of variability. But in general, moving at just those 20 meters actually often makes. These show some of the averages. Actually, I realized when I was looking at this recently that one of the wrong plots. But the one on the top is the afternoons. The one on the mornings looks a little bit nicer. So just all of them averaged together. Between 20 meters and 40 meters on the right-hand side, there is pretty quite a drop. And then if you go further, it usually gets better until about 80 meters, 100 meters. You go beyond that, so things go up again. But there are pretty consistently significant improvements between 20 and 40 meters. This shows the cumulative distribution, basically where the observations are in terms of concentration. And basically the background concentration at 20 meters and 40 meters is pretty much the same. But what's different are the very high concentrations. You get more high concentrations near the intersection center than you do near a little bit further away. So most of the benefit is actually accrued from being exposed to less puffs of high concentrations. And this is the result from a very simple exposure time duration model, where we imagine a transit user getting off of a bus and walking to the bus stop that is 20 meters away versus 40 meters away, and what happens to their exposure to roadway pollutants. And so if you move, if the intersection is not higher than the area around it, then walking further will expose you to more. But generally it is higher, and generally the region that we observe is in terms of actual observations is in that purple region. And so, and the different lines are a little bit different. If actually some of them are for moving it to 60 meters. And a little bit different walking speeds. But basically the reductions in exposure are from making it slightly worse, -10%, to about a 50% reduction. So it can be a fairly significant impact just by moving the bus stop another 20 meters, and then people walk a little bit further. That's good too. Okay, so I originally had just a summary for planners, but I was asked to put in a science summary, so I'm basically going to do the summary twice. Okay, so in terms of the science summary, we have a lot of mobile data, and they offer many advantages as a data collection strategy. Certainly, stationary has lots of advantages as well, but taking advantage of basically you can make maps with them, which you can't do at least until we get really cheap sensors and have a really cheap way of collecting that data. It's hard to do with stationary monitoring. But the high spatial resolution presents special challenges to data processing, needs to be dealt with carefully. And the microdynamics model can successfully reproduce pollutant concentrations at a highly detailed level and can be used to probe impacts of particular events and traffic control strategies. Exposures of transit users could be lowered substantially by moving the bus stops from about 20 meters to about 40 meters from the intersection. In the case of street canyons, or if you just want to look at a street level by itself, the simple building weighted height street aspect ratio can be used quite successfully to estimate the impact of different designs on pollutant concentrations. And this is on quite solid ground, I would say, on significantly more solid ground than the more neighborhood approach that we have that I talked about, which is this one. So for more complicated urban configurations typical of California cities, morning concentrations, which are typically the highest, appear to be governed by the areal aspect ratio, which is the area weighted building height divided by the fraction of open space over a several block area. But again, I think this really should be further verified. Afternoon concentrations appear to be governed by the vertical component of the turbulence, which appears to be enhanced by building heterogeneity, so implying that heterogeneity may be good. And yeah, deserving of further study. So the summary for planners, areal aspect ratio, which combines building area weighted height, building footprint, and amount of open space, is something that controls or seems to govern concentrations in the mornings, and lower building volumes and more open space result in lower pollutant concentration. And the size of the effect is approximately up to a factor of 3. This is really appears to only be important under calm conditions and not critical when the atmosphere is unstable. So building heterogeneity seems to have the potential to also have an impact that's approximately a factor of 2. This is more important under unstable conditions and not important under stable conditions. So unfortunately in cities we got to deal with both, although if you have to choose, I think you should go for the stable. Govern concentrations in the mornings. So in terms of traffic flow, lower traffic flow is better controlling for fleet mix, cleaning up the mix. Huge across the board benefits. And traffic flow is improvements. In terms of traffic management, fewer stops and smaller queues reduce emissions. Amount of traffic. We can't really estimate, well, maybe we can estimate it. We haven't estimated yet the size of this effect from our data. And bus stop sightings, moving the bus stop from about 20 to 40 meters can make improvements that are actually up to about a factor of 2, but more typically in the 30 to 50% range. And then from other studies, but we have a lot of research to back this up, further away from highways, citing particularly sensitive uses like schools, or the elderly and hospitals and so on. Parks further from highways is better, and under daytime conditions, 500 feet is quite sufficient. Under areas that are affected by early morning larger, and these can also be a factor of 2 up to 4. That I will stop, and except to recognize again the people who really did the work, especially Wanchik Choi and Dilhar Ranasinghe and J.R. Desheza and Lisa Wong. There was also significant help from Steve Mara and Kathleen Kazawa and Toshi at ARB, and Steve and Kathleen especially with help with the mobile platform. And some work was also done by, so the earlier data was collected by Dr. Shishan Hu, who also works for ARB. And a lot of other work was supporting the UCLA results from Karen Bunavich, Rodrigo Sigel, who is a visitor from Chile, Arthur Weiner, Mario Girla, and Brian Taylor. And then at Riverside, CTAN, probably now Dr. CTAN, I guess. Spent a lot of time with Nico in the field, and
All right, I've been told I need to start again. So, well, thank you. This was a really insightful and interesting presentation. I had a question about the UCR VDM tool and its application relative to elevated and below grade roadways, which are a frequent occurrence in, highly urbanized settings. Does the model or can the tool accommodate those as yet, or would that be a add-on at some point?
So right now the tool does not account for that. There are other tools that EPA has developed that they did studies on the impact of elevated roadways, depressed roadways on the resulting near road concentrations. So I would refer you to look at those tools if you're interested in that type of tool. But right now VDM does not, and yeah, so it would require significant additional research to implement that in VDM.
So it'd be really looking kind of holistically at a landscape if there was a portion of elevated roadway, and then that you would need to factor in, I guess, potentially both models, or?
Yeah, so I mentioned that I think a practical way to do this using tools we have now would be to combine VDM with AirMod. So AirMod can, simulate dispersion from roadways, and there's new research that EPA has been doing to, to study the effect of the elevated roadways on the resulting concentrations. And so I think that those tools would give you the estimate of the effect of the elevated roadways. But VDM really adds the component of when you're in the city itself and there's buildings directly next to the road. I mean, that's the situation that VDM is describing. So essentially, if you had an elevated roadway kind of located further away from your street canyon or your street with buildings next to it, you can use these other dispersion models to calculate the concentration from that roadway, and then you add on the VDM contribution. But VDM is only describing the contribution from the roadway that you're specifically on and due to the buildings next to that roadway. And so, yeah, I would refer you to, AirMod, and there's this new kind of research version called R-Line, which is implementing those new research results on elevated and depressed roadways.
Like for a below grade road,
Yeah.
it's possible that you could add just the elevation difference between the road and the structure, the height of the building.
Depressed roadways are major highways, kind of. I mean,
A
there
lot
are
of them, but I don't know.
occasionally
I
a
know
little
of
bit in
several
urban
instances
areas.
where there's schools right next to like a sound wall and a highway beneath. So I mean, it's not that atypical. I don't.
You're talking about like like in an urban area.
Yes,
Okay.
I was just curious. So.
With reference to your question, I know that there was work done by Tom Cahill at UC Davis back in the 70s when there was lead in gasoline. That was a good way to track on things. Pressed roadway that you have a chimney effect. Roadway exposures are much less. Down, I think, 500 feet or more. I was wondering about, I was over at the Cigarette building in West Sacramento. It seems like that would be a good design for a building that would step back like that as it goes up.
What? I don't know this.
Like that would be a good, if you're going to have a tall building, that'd be the best way to go.
Wow.
Hi, thank you. I appreciated the science and the humor, just to let you know.
Thank you.
But I do have a question. When you're thinking about the 500 feet, and I know that, looked at studies and you've looked at studies, there are effects beyond that that seem to be. But have you any sort of assessment of how topography figures into that? Something about the built environment that would tend to farther, and I guess probably relates back to the elevated.
I could take a crack at that. I mean, I think that if you don't have buildings and you have point source pollution, then it disperses much more quickly and in a narrow plume. But if you have buildings, it gets spread around a lot. So the buildings definitely, as the wind channels around the buildings in ways that sometimes are perpendicular to they're often quite perpendicular to the flow, it definitely expands the plume tremendously.
So if you have, intersections. That could tend to channel the plume.
Yeah, and we can actually see that in our data. I didn't really show that much, and we've been kind of trying to model it with, but yeah, yeah, it's an excellent point, definitely.
Right, so there is actually one question from the web from Brian Frank, Division of Air Resources Board, or Air Resources in New York State Department of Environmental Conservation. The question is, the presentation includes data obtained with both multiple stationary instruments, quote, Riverside, unquote, and with a mobile platform. Can you speak to the relative usefulness of these two approaches, especially in terms of obtaining data for validating the models that were being evaluated?
Hey, that's a great question. So I think for the evaluation of the models that we had presented, I think usually the stationary monitoring is probably a better choice because this type of model evaluation requires you to get, stable average values that you can predict with the model. And so the mobile monitoring tends to give you these kind of instantaneous concentrations, which are very hard to predict. And so really you want, just due to the nature of the variability of emission sources and turbulent dispersion, you want to average over several events essentially to really get a stable average for model evaluation. And so I think the stationary monitoring will it's easier to do that with stationary monitoring. Also, I just want to caution with the mobile measurement, I think the analysis is not as well developed. So for example, stationary, people have used this approach for a long time for understanding, atmospheric pollution. And so it's very well understood, but analysis of mobile data is not as well understood. There's still questions about how, like, for example, how many repeated runs do you need to get that stable average if you wanted to do concentration maps, for example, and we don't really know. And I also want to caution that with mobile measurements, you can be potentially biasing your result depending on what you're trying to do. So because you're following specific vehicles or you're kind of following like fleets of cars, it could give you a different result from what a stationary monitor would. If you had many stationary monitors to give you a map, that could be different from what a mobile monitor would tell you, just because of the nature that you're following specific vehicles around. And I think for these type of field studies, if you had the choice, I think the reason that you would go with mobile would be mainly due to cost, because if you couldn't, buy enough stationary monitors or it was too expensive to deploy them, maybe you would choose mobile. But I think, so that's probably the main benefit of mobile monitoring, is that it's easier to deploy in urban environments and probably lower cost. But you have to be really careful about the data analysis. And I think one place where it's actually very useful is for measuring emissions, so mobile source emission measurement. Sometimes you do want to follow specific vehicles, and you can get emission factors using the mobile monitoring like that.
So let me address that as well. So I think that that stationary monitoring is very traditional, and so everybody's very comfortable with it. I think that there are some significant advantages. There are advantages to both, but one of the advantages to mobile monitoring is that you can really screw up stationary monitoring especially if you have only a small number of monitors. And for example, there have been some studies around freeways that have shown some kind of curious results. If you have a single stationary monitor and there's something nearby that is producing that pollution that you don't know about, you just have no way of knowing. If you do mobile monitoring, you have a map and you can see where the hotspots are very clearly. So I think that especially for monitoring around steady plumes, then like around freeways. Mobile monitoring has very significant advantages. Also, you couldn't do a study like the looking at where the bus stop should be, because you just, you know, maybe someday we'll be able to get a monitor every 5 meters, but that day hasn't arrived yet, and it's not going to happen next year. So, so I think with creative approaches, mobile monitoring has lots of really great applications, especially as we get more access to more instrumented mobile vehicles. I think it's a very, very exciting future. And also, as we start to develop or make more progress in developing more complex urban models, we should be able to apply those to two-dimensional maps, which are things that we can get from mobile monitoring, which will be really exciting, I think.
And I just want to add a couple of points to that. Our perspective is that it is a portfolio approach. There are strengths in stationary monitoring, which actually gives you better temporal resolution, continuous measurement, which offers better temporal resolution. But at the same time, spatial, you have to, as of now, we believe that using mobile data is going to give you better spatial resolution, and it's a combination of the two. So as you develop the models, if you just have stationary monitoring, it won't give you what happens within communities, and it won't give you information about hotspots as they occur in real world. So it is a combination of the two, and both data sets offer certain strengths, but if you combine them, I think it'll be a better solution.
Yeah, I just have to say I completely agree. The biggest pitfall of mobile is that you can't do it 24 hours a day. So you have much smaller windows, and you can leave the stationary measurements out 24 hours a day, which is really huge advantage.
Thanks. I was wondering, thinking of some studies done in London with personal monitoring. Where do you see mobile monitoring done with pedestrians or bicyclists kind of fitting in to this approach?
I think that's great. I mean, basically, it's almost the same. It's slightly better because it's actually where the actual person is. With a mobile monitoring platform, Steve and his colleagues have put the inlet as close to where a human would be on the sidewalk as it's possible to be. So we're trying to get that. But if you're walking around, you're actually obviously doing it the way a real person would experience it. But the way that I think about it is that it depends on the relationship between the temporal resolution of your instruments, how fast your instruments are, and how fast you're walking or driving. So if you have a 20-second instrument, it's not very useful on a car, but you can use it on a person or on a slow cyclist. So it's just kind of the combination of the time resolution of the instruments and the vehicle.
All right, thank you, everyone. With that, I would like to thank the speakers once again for all their knowledge and expertise on this field, and would like to close this research seminar. Thank you, everyone.